Laws of exponents. Laws of exponents are very important and we must remember them always because they allow us to manipulate and simplify algebraic expressions. So here's all the laws. You have to remember them forever and ever, and I briefly go through them. So if we have two powers multiplied and the base of the powers are the same, then the result would be base to the power sum of the indices. If we have a quotient of powers and the base again is the same, then the result would be base to the power of the difference, power of numerator minus power of denominator. This is important. The order of this index is important. Next, if we have power raised to another power, then the result would be our base times product of the indices. Next, number to the negative power would equal 1 over the base to the positive power. Yes, here we have minus m, here we'll have m. Next, this is powers, fractional powers. So we have something to the fractional power, rational fractional power. Then the result would be, so we draw a third sign, and under the third we have base to the power of whatever we have here in numerator, and that would be nth root. So here we'll write whatever we have in denominator. Next, exponential law. So if we have product raised to a power, it would equal to corresponding product of corresponding powers. Similarly, if we have a quotient raised to the power, then it would equal a quotient of corresponding powers. And finally, that's very important, any number raised to a power of 0 would equal 1. What's important to remember that these laws, you have to be able to recognize and use them from left to right and from right to left. Again, these are your tools to simplify algebraic expressions. And next we are going to apply these laws of exponents. So have these laws in front of you and follow my examples. So we have a product x to the power 5 times x to the power 3. So base is the same. That's the first thing, very important. So can apply exponential law. So it would be x to the power of sum of these indices, 5 plus 3 equals x to the power of 8. Next example, we have a quotient of two powers and they both have the same base. Can apply the law. Okay, quotient is the base to the power of difference, power of numerator minus power of denominator. 3 minus 5 equals y to the power of minus 2. And often you'll be asked to provide your answer without negative powers, and that would allow us to use, I believe it's third law, that would be 1 over y squared. Next example, a to the power 3 and to the power 4 would be what? According to exponential laws, we have a to the power 3 times 4, which gives us a to the power of 12. Excellent. Now, x divided by y to the power 4, well, we know that would be simply quotient of corresponding powers. Now, these examples are more interesting. So when you have something like this, for example, this example, so basically you write every prenumeral, yeah, so these letters, we call them prenumerals, and collect the powers. So, for example, first is a, okay, and here's a little bit of trick. So we'll rewrite ax squared first, and you see here we have ax to the power of 3, and I almost missed it. So first we open these brackets, and that will give us times a to the power of 3 times x to the power of 3. And now, when they open all the brackets, we can collect powers for the same prenumerals. So a will get us a to the power of 1. So we don't write usually power of 1. So it's omitted. So to the power of 1 plus 3. And then we have x to the power of 2 plus 3. And the result is a to the power of 4, x to the power of 5. So looks simpler than what we started with. Next example, it's probably rather from times when we didn't have calculators, so I had to use different tricks to calculate less manually. So we proceed separately with numerator and denominator. First, we'll open these brackets. We'll have 7 to the power of 4 times 2 to the power of 4, that was numerator, over 7 to the power of 3 times 5 to the power of 3. Then I observed that numerator and denominator have 7. Okay. So I collect powers for 7. I'll have 7 to the power of 4, that power in denominator, minus 3 times 2 to the power of 4, leave it as it is, over 5 to the power of 3, and that simply gives me 4 minus 3 is 1, which is 7. So it would be 7 times 2 to the power of 4 over 5 to the power of 3. And then you can proceed and evaluate those. So, and the last example. So again, it's a little bit tricky because we have product with the power and to the power. So do one step at a time. So first we open the brackets here, applying law of exponents. That gives us x squared times y cubed squared. Now we proceed to denominator. What we'll have? X, rewrite as it is, then we have, okay, here we can simplify already. Y squared raised to the power of 4 would be simply y to the power of 2 times 4, 8. Continuing. So now we can start collecting powers for the same prenumerals. We have x in numerator and denominator. Numerator gives us 2, denominator gives us 1, minus 1, times y in numerator has power, so y cubed to the power of 2 gives us y to the power of 3 times 2, 6. And in denominator we have 8, so that would be minus 8. And finally we have x to the power of 1, y to the power of minus 2, or leaving your answer without negative powers, we'll have x over y squared. What is scientific notation? Well, in science, we deal with very large numbers or very small numbers, and sometimes it's very difficult to even understand what sort of number it is. For example, average cell contains that many molecules. Can you read this number? Or diameter of electron is this number. Very small. We can see it, that's a lot of zeros, but actually how we compare those numbers and understand how small or how big it is. That's why we use scientific notation. That is to present number in this form. N, which is between 1 and 10, times 10 to the power of k, where k is integer. That is, it can be both negative or positive. For example, let's present in scientific notation 690,000. So this number we can read, but I mean, that's why I choose it, so we can comprehend and show a meaningful example. So start trying to present it in this form. Start trying to present it as follows. For example, 690,000 is same as 69 thousandths times 10. So for every zero, we basically have 1 power of 10, and essentially what we do, we're moving our decimal point on the left. Okay, let's continue this process. So let's make this smaller. So we'll have 6,900 times 10 times 10. So, and continuing this process till this number becomes within the range 1 and 10. So basically what we do, for every 0, we have power of 10. So here we have 10 square, and how many tens we need? So square, cube, 4th degree, 5th degree. So that's simply 6.9 times 10 to the power 5. Now, we have this small number, and essentially we want to move this decimal point on the right. Yep. Okay, let's start this process to understand how it works. Okay, this number is the same as 0 point, and now we'll have two zeros here before 7. 0, 0, 7, or 4 times 10 to the power minus 1, or divided by 10. So we know when we divide by 10, number becomes smaller, and we move our decimal point on the left. So basically, that's same thing, same number in different form. Continuing, I want to move my decimal point on one more place on the right. So that would be 0.0704 times 10 to the power minus 2. Now I'm dividing by 10 square or 100. So basically every place I move my decimal point on the right corresponds to 1 negative power of 10. So we already have minus 2, and we need to move decimal point to 2 places. So that gives us 7.04 times 10 to the power minus 4. Okay, that was example how we bring numbers to the scientific notation. Now, if we are given number in scientific notation, we need to be able to write this in general notation. Okay, so we have 8.53 times 10 to the power 6. All right, so what we do, so basically every time we multiply by 10, we move our decimal point on the right. Okay, let's start this process. It's the same as 85.3, so we use 1 over 10 times 10 to the power 5. Or, and so you see, and we can again make this larger and use 1 of our tens. It would be 853 times 10 to the power 3 equals, and that's 1,000. Basically, every time we move a point on the right, we add 1 place and move our point on the right. So that would be 853. Basically, all our numbers, meaningful numbers, are finished. So we add zeros. So we need 3 places. 1, 2, 3. And this is where we add zeros. That would be 853 thousandths. Similarly, when we have negative powers, so we'll be moving our decimal point on the left. Okay, let's move it just 1 place on the left. So it would be 0.916 times 10 to the power minus 2. We used one of the negative tens. Okay, and if we keep moving for another 2 places, so what will happen would be 0 point. So we'll simply have to have 2 more places in front of decimal point. 0.0916. That's it, and that's how we use our index laws for scientific notation. Okay, so everybody does mistakes, and obviously in this number I did a mistake. You see here I have 85.3 times 10 to the power 5. Then I use one of the tens and put power 3, which in fact should be 4. And that means that the final answer, like in 1, was 0. So in fact, the answer would be 8,530,000.